I like to get started just asking you, how did your study come about? Is this part of a larger study that you're looking at, or how did this get started?
I don't know if I would say it's part of a larger study per se, but it may be like a series of just inquiries into trying to understand how the gut microbiota and exercise interact, for lack of a better word. We did these earlier studies where you look at, the kind of place to start, which is, okay, does exercise affect the gut communities, right? And so there's lots of that. It's just like, okay, if we consistently note that, the gut and the host are in this symbiosis, then hopefully it also works in the opposite direction. Not only does exercise, help, augment these good gut microbes, but then how does the presence and or absence of the gut microbiota affect exercise performance? And so, we kind of refer to that, as I've been saying, like it's this bi-directional, right? It goes in both ways. It's kind of like the reversible reaction. It can go one way, it goes the other way. And so we knew that there was very limited, but some, things out there just simply suggesting that in, germ-free mice, which are the mice that have no microbes, that there is this reduction in exercise performance. So, we just from there started thinking, okay, what do we have access to? And it wasn't until more recently that Rutgers had access to germ-free facilities, and we have 3 campuses, so not at my campus per se, but the next best thing is to use a cocktail of antibiotics to try and eliminate the gut microbiota, or at least to a great extent as possible. And so the idea was just to simply, we had this model of enhanced exercise capacity that we had published, what their gut microbiota looked like in 2019. And we noticed that, not only did it have a gut microbiota untrained that was similar to a wild type mouse that had been exercising for several weeks, but then when you further train this mouse model, it had even more of a microbiome that suggested, that exercise was playing a role in its phenotype. So we're like, okay, well, how much of a role is it playing in this phenotype? And the model had been worked on by one of my collaborators for quite some time. And so we had ideas of targets that we could look at if we administered the antibiotics. So we knew SIR2 and PGC1 alpha, and markers of mitochondrial oxidative phosphorylation were higher in this animal model, and then again higher still when exercise trained. So to us, it seemed like a very logical progression in, a series of studies that my collaborator had, initiated, but then continuing with the microbiome as a focus, since, like I said, we put the 2019 paper out. So we just simply said, okay, what do we think antibiotics is going to do after we've trained this mouse model? We know it should do A, B, and C, right? And then so you have you take the samples post the exercise training to confirm, your previous work. And we did, and then we gave them antibiotics for a week and continue training them, just so that you don't confound the study by not training them and seeing what's going on, and just simply observing, what happened during that week of training. And then after, you take all of the tissues and so forth. And we noticed that, after that 1 week, their exercise training was significantly reduced. And, and we started, we reported all of the wild type mouse data in this manuscript in MSSE. And then we just, again, started looking at what does citrate synthase look like, and then complex 4, and then nitric oxide, because we know those are major regulators of mitochondrial oxidative phosphorylation. And then when you see they're low, we're like, well, that's the stimulus for mitochondrial biogenesis. And we know that that's another mechanism. So let's take a look at those proteins. And they were also reduced. And it was just kind of, it was really exciting just to see, there's been all of these proposed links between the gut microbiota and lots of tissues, right? Brain is probably the one that most people to date are most familiar with. But I think that there's this increasing interest in how the microbiota is linked to skeletal muscle, and in particular mitochondria, because mitochondrial, if you go back to, you know, early studies and just how they've evolved, they've seemed to have evolved from bacteria. So it would seem like a natural link between microbes and mitochondria. So that's kind of.
So I'm fascinated by the microbiome. I know the implications that it has. So definitely was super cool reading about it. When you were doing the experiments, so basically you started with the mice, and then you train them the first week, everyone, you train all the mice, and then you have some time passing, or you keep training them each week.
Right. So you test everybody to begin with before any of the training starts, just to get an idea of what their baseline is, you know. And then what you do is gradually from there, you go through a titrated protocol, you know, similar to what maybe you should do with humans, as you start them off at, you know, this speed and this grade, and then you gradually work that up over the course of the first, you know, few weeks, and then maintain that for the last few weeks of the duration of the training period, which in this case was 6 weeks. If you really want to say, you know, it was technically really 7 weeks, because we did train them during the week of their antibiotics. So that's how we do. And then we do post testing, right? So you do post testing after the 6 weeks of training, and then you do another post test after the week of antibiotics.
Okay.
So there's, you know, the 3 kind of time points. So that's what we named in the paper. You'll see it's pre, post, and then ABX or post ABX. And so that would be those time points. It would be basically after 6 weeks of training, and then after 1 week of antibiotic treatment.
What did you find, and what are the main implications?
So the most recent paper in MSSE shows that antibiotic application to the animal model that we showed during their exercise training produced results that show that there was a significant reduction in mitochondrial oxidative phosphorylation, and subsequently mitochondrial biogenesis, and also alterations to hind limb blood flow, which, you know, are 2 of the major mechanisms associated with increases in exercise training, right? Blood flow and mitochondrial biogenesis. So we were, you know, excited to see that it appears that the microbiota might be involved in these mechanisms of exercise training and their adaptations.